Welcome to qnawire.
So let's draw the free body diagram. We have the ball. Oh. Okay. We're going to say that this would, of course, be the radius. Going straight down would be mg. We have the ball is on a surface. Going straight up would be the force normal. Going straight to the left, opposite to the direction of motion, would, of course, be force friction. We're going to say that there's a force acting on the ball. We're going to denote this as F. This height we're going to denote as H. And so this would be the full free body diagram for the ball. We can draw our Cartesian axes, y and x. And then we're going to say that clockwise torque is positive. So clockwise is positive. We can apply Newton's second law and then the sum of torques. So we can say sum of forces in the y direction would be equal to force normal minus mg. This would equal 0 because the ball has translational equilibrium in the y direction. Therefore, force normal equals simply the weight of the ball. We can say the sum of forces in the x direction would be equal to the force minus the force of friction. This would be equal to the force minus the coefficient of kinetic friction times force normal. And so we can say that the sum of forces would then be equal to the force minus the coefficient of kinetic friction times mg, the weight of the ball. And this would be equal to the weight of the ball times the acceleration of the ball itself. Therefore, the acceleration of the ball would be equal to the force applied divided by the mass of the ball minus the coefficient of kinetic friction times the acceleration due to gravity on Earth. And so we can say that the sum of torques now is going to be equal to the force times h minus r plus the force of friction times r. This is going to be equal to the force times h minus r plus coefficient of kinetic friction times the weight of the ball, mg, times the radius of the ball, r. This will equal the moment of inertia of the ball itself times the angular acceleration. Therefore, the angular acceleration would be equal to the force applied times h minus the radius of the ball plus the coefficient of kinetic friction multiplied by the weight of the ball times r, all divided by the moment of inertia of the ball. We can say that the velocity of the center of mass is then going to be equal to the velocity initial plus the linear acceleration times t. This would simply be equal to, we know that this is going to be 0, so this would be equal to f over m minus mu sub kg multiplied by t. Omega would equal alpha t, knowing that the initial angular velocity is 0. So omega, angular velocity, would be equal to f times h minus r plus mu k mgr divided by the moment of inertia of the ball times, again, t. We know that the ball is rolling without slipping. So we can say that omega is going to equal the velocity of the center of mass divided by r. And then we need to solve for the value of h such that when the ball loses contact with the pushing stick, the ball is rolling without slipping. So we're going to call that time of release. And we're going to say that the angular velocity equals the velocity at the center of mass divided by the radius of the ball. And we can say that this is going to be f times h minus r plus mu sub k mgr divided by the moment of inertia, I. This would be multiplied by the time of release. And this would be equal to 1 over r times f over m minus mu sub kg times, again, the time of release. And so we can say that h would be equal to 1 over f multiplied by the moment of inertia over the radius of the ball times F over m minus mu kg minus mu k mgr plus f r, close parentheses. Again, this is going to be capital M. And then solving for h, simplifying, essentially just simplifying this, we have that the height would be equal to 7 over 5 times r over f, the radius of the ball, divided by the force applied, multiplied by the force applied minus the coefficient of kinetic friction, multiplied by the weight of the ball, mg. This would be our final answer. That is the end of the solution. Thank you for watching.